So I'm very happy to introduce Juan Miguel Arrazola. So Juan Miguel is an old friend of mine. We overlapped at the University of Waterloo, where Juan Miguel did his PhD with Norbert Lukenhaus on quantum cryptography and related topics. Juan Miguel then moved to Singapore, where he did a postdoc with Valerio Scarani. And then he moved from Singapore back to Canada, to Toronto, where he is currently working with the startup company Xanadu. And we're very happy to have Juan Miguel today talk to us about what Xanadu is up to and also hopefully give us a demo. So, Juan Miguel, please take it away.
Thank you, Patrick.
Mhm.
Yeah, I had a nice time remembering all the lunches we had with Bangladeshi food at Waterloo
Yeah,
in
good stuff.
preparation for this. Yeah, so hello everyone. It's great to meet you. Thanks again for the invitation. I'm actually really excited about this particular talk because it's the first time showcasing access to the cloud. So I'm particularly excited about this. It's a pleasure to be here. So again, my name is Juan Miguel Arrazola. I'm a theorist, theoretical physicist working at Xanadu. I'm part of the software and algorithms team. And to a big extent, the focus of my work has been on algorithms and developing applications of our hardware, but also alongside software development, right? Which is a big philosophy of the company, as I'll explain in a while. And I'll just get started. So thanks again for the invitation. Really excited to share some of our work with you. I want to start talking about the company. I've noticed that there's only so much that you can actually learn from the website and maybe news articles. So I want to give you like my personal perspective of what we're doing and where we are. So companies are people, really, in the end, and I'm confident in saying that we have an extraordinary team, especially for a startup. It's a team that's been growing. So when I started in 2017, which is like really the first cohort of people and full-time employees, Tom actually started maybe a couple of weeks before me. So we were some of the first people that joined the company. We were about 10 or so, and now the company's more than 60 people. So it's been a nice linear growth since the beginning. Roughly speaking, the company is divided into four main teams. So there's hardware, which is the core and the center of everything that we do, and that's led by Zach Vernon, who's a graduate from U of T. On the software side, and this is software in the general sense, so it's also about algorithms, right, and more theoretical aspects. Also like very traditional software development, but also this quantum software aspect of things. So that's led by Nathan, and I'm a part of the group. So Nathan, who also I think someone that Patrick may have overlapped with before. There's also like an intermediate group between like very theoretical aspects and hardware aspects that we call the architecture team. So they look at, to a big extent, theoretical aspects of the hardware, not so much on the side of like quantum optics, but on the side of design, on the side of error mitigation and correction, and like more abstract kind of aspects, right? And then there's a team that's like focused on everything else, both business sides, but also like the platform for cloud access. That's led by Raf. So we have a really nice team, and most people are PhDs. So like I guess many people in the audience right now either are or are on their way becoming. So very technical team with a lot of support on the business and like management side as well. We have also outside advisors and a lot of ongoing collaborations with academic and industry partners around the world. So this is the overview of the company and its people. And again, also people from all around the world. It's really more than 15 nationalities, which is something that's really great about working here. Something that I like to share when discussing Xanadu is the mission statement. So this is something that is relatively standard for companies to do, and oftentimes it's just a bit cliche, but I generally really like, and also the thought that has been given to Xanadu's mission. So I'm going to read it. It's to build quantum computers that are useful and accessible to people everywhere. And I want to break it down to some extent. So first, at the center of this mission is the technology, right? And the fact that it's a hardware company first. So the core of everything we're doing is to develop new technologies and new quantum technologies, right? And so this is encompassed now with the term of quantum computing as the main driving force, but really it's good to think of it a bit more generally, right? It's about building quantum technologies. But it's not just that, it's also about them being useful, which is very challenging as well. So not only building them and developing is challenging, but also understanding how they can be of real value, right? And for different people in different situations. And that encompasses also implicitly this aspect of software, right? In the sense that we want to understand what to do with the devices. We also want to understand how to program them, how to control them, and how to extract the potential that they have, right? So that's kind of like where me and people in the team can contribute. And there's an aspect of accessibility that's very important, and I will touch upon this as well, where not only do we want people to actually use these devices as like you in the audience are able to do so, and as I will demonstrate later in the talk, but it's not just the hardware itself, but everything that we do, right? So there's a philosophy of openness as much as it's compatible with also the business side of the company, which they are very compatible, to make it accessible and to make it accessible widely, right? So it's not just for a few, perhaps high-paying customers, but generally speaking for, but sorry, I want to turn something off. Let me go back to present. But also to as many people as possible, right? So and at the core of this is the idea that we can make more progress if we open the ideas and if we allow contributions from everyone, right? So again, the fact that I'm here giving this talk is a testament to that, right? Like we want the whole community, right? And particularly now as first users, people that have quantum expertise to have access to everything that's happening in the company. So that kind of sets the tone for what's going on with Xanadu. Let me give a bit more details about on the product side and what's being developed. So like I mentioned, at the core, it's the hardware, and it's the building blocks, right? The platform is photonics, right? So this is a decision based on both its potential, but also expertise for people in the company and the founders. And the main driving force is to develop photonic quantum computers, right? That's the end goal. That's what we're working hard towards. Everyone in the company, right? And in the near term, this takes the form of Gaussian boson sampling. That's the form of the near-term devices. And again, as part of the company's philosophy, this is something we're making open for everyone. It's really a stepping stone towards more powerful and more general and closer to universal systems. But it's the form of the near-term devices. But the technology that goes into permitting even these near-term devices to exist, they all spread even beyond, right? So a lot of the components that make up photonic quantum computing can be used in other aspects of quantum information and quantum communication, right? Like randomness, QKD. And there's some talks about how to commercialize this inside of the company. There's also just on the side of sensing, and in particularly the ability to detect photons, which is generally very useful, and it's a state-of-the-art technology that we employ. There's also a drive to potentially commercialize this. So that's the core of the hardware and the technology, but supporting that there's software as well, right? And this gets perhaps best embodied in terms of the software libraries that have been developed at Xanadu. So there's PennyLane, which I believe some of you are already familiar with, and that will be the topic of Tom's talk later today, so don't miss it. And this is thinking broadly about quantum computation, right? So in a sense, every company that has a hardware play, right, requires some software support, and you have to make a choice in terms of what platform to build your devices in, just because it's so intensive to pursue one in particular. But software is much more versatile and much more abstract, and so we understand that having such a strong team, we want to make the software as widely impactful as possible and useful for the community. So that's really embodied in PennyLane, right? But then specific to photonic devices, and in particular as the interface with hardware, there's StrawberryFields, and in particular the creation of the Xanadu Quantum Cloud, right? So how do we interact remotely with the hardware that's being built? And part of this talk will be to showcase that. So this gives you a picture, right? And people outside of the company fall roughly working in some of these core areas. It's a bit of history. I'll be very brief here. So again, the company was founded in 2016, but there wasn't anyone. There wasn't any money, really. It's just like a Christian, our founder. And some of the core components of what is now on what we built the company on top of, which was a demonstration of squeezing on chip that was happening early on, right? And also like the first versions of our software. So that happened in the early stages, and that was a big drive of everyone working at that point. That really helped us to kind of validate the whole vision behind the company, and therefore have investors share in our optimism to have the first rounds of funding. So there was a seed funding of around 9 million. That was partly, for example, paying my salary. There's a lot of collaborations also. Maybe the main one has been a partnership with a project with Scotiabank and BMO. So it was one of the first sources of income for the company. And as a big milestone, the actual hardware lab opened in 2019. So this is very important because what you're going to see now, when we access and we sample from the device in the last part of this talk, that is the result of work that's happened in maybe a year and a half. So there was no lab a year and a half. We had to dismantle the initial things and then move everything into a new lab and really start hiring people. So the kind of like rapid pace that happened in a year, that's something that I want to share to have as a, as a reference in terms of future progress as well. And so these milestones really led to us being able to have a Series A that really like fueled the ability to scale and to be more aggressive in the pursuit of our goals, hire more people. So that happened early in 2019. Since then, there's also additional money coming in the form of grants, and there's different generations of devices. So the initial one that's been prototyping internally had 4 modes. The one we're going to access today is 8 modes, and there's already work for 12 modes, 24 modes, and to continue, right? And even though there's not an official launch of the Xanadu Cloud, that will happen later this year, or maybe next year. And but we can still have remote access to the devices. It's a big milestone for the company. It's a bit of the history. I want to touch briefly on like these main areas of hardware and software. So this is an example of the current generation of software. So this is all based on nanophotonics and integrated photonics. So it's this idea of being able to essentially take what was traditionally optical tables in basement labs and universities and really miniaturize it into a chip that fits in your fingertips, right? And so a lot of the efforts come into the design of these chips, right? But once those designs have been nailed, and we have a whole team that's focused on chip design, they can be sent off to foundries that can fabricate them and particularly can scale them up and produce them massively, right? So it's really integrated photonics at the core of the technology. And at least for the first generation of GBS devices, the operation of the devices can be essentially divided into the generation of squeeze light, which is done with micro ring resonators. So this is cutting edge quantum optics. And it's something that I particularly as a theorist just love in its simplicity. So I don't know if you can see my cursor, but on the left-hand side of the of this lithograph of the device, there's those little rings, little circles, and that's it. It's literally you edge a circle next to a waveguide. It's a straight line next to it. Of course, there's a lot of detail and it's a lot of engineering that's very difficult that goes behind it to get everything working properly. But that's the magic of being able to generate on-demand, deterministic, highly squeezed light. And this is the source of photons for computation, right? And then following that, it's the ability to actually entangle and have these modes, so quantized electromagnetic fields, right? Interact in the form of an interferometer, and this is fully programmable, right? So we have squeeze light sources and programmable interferometers that together make up the basic circuits of this photonic quantum computer. So the special purpose photonic quantum computer. Everything is digitally controllable, right? As you'll see, and we can program this remotely. And in particular, the interferometers are fully universal, right? At the end of this, there's slide that we detect using photon number resolving detectors. So in-house at Xanadu and currently in development, it's going to be the largest collection of photon number resolving detectors because we want to probe all these modes for their light and we want to be able to count photons. This is cutting edge technology. This is the main picture, and the idea is to scale these up to improve them, produce them massively, and then kind of flip the switch to start unlocking additional capabilities that get us closer to not only like universality in quantum computation, but also potentially the building blocks of error correction and fault tolerance. And the software, again, I like to think of it in terms of the two libraries. So there's StrawberryFields, which is going to be the focus of this talk, and then you can find all information in its website. So this is a snapshot of what you'll find if you actually access. I really invite you to do it. It's fantastic documentation all throughout. If you haven't done it already, I really invite you to do it. There's also Penny Lane. So it's really the two sites. There's the one that speaks to hardware, the photonic aspect, and on the more general framework for quantum computing, based upon the idea of differentiable quantum computations. And they each have their dedicated websites full of fantastic content. And again, I really invite you to take a look. Something that I'm particularly proud of that we do, and again, it's in accordance with the mission and the philosophy of the company, is that there's an openness of sharing our insights and our work, and also as a testament of the quality of the team. It's really fantastic work that has happened. So we have, since in the last 3 years or so, it's more than 50 papers either published or available on the archive, and it's really high quality, really impactful research. Maybe some of you already have stumbled upon some of our papers in the past, and it's a big component of what we do. And so indeed, to give you a bit of a timeline for the vision of the company, there's a big component of just doing the research and development initially. So we need to get these building blocks right. We need to get the software to be extraordinary, right? We need the hardware to demonstrate its basic capabilities and to show how they can be scaled and to what extent they can be done. And that requires a lot of research, a lot of problem solving, right? A lot of design engineering. And to the extent that this continues to be successful, there's a next stage where we can start commercializing and turning these into products as much as possible, right? And that's kind of where we are beginning to be at this stage. And of course, the long-term vision is to continue to grow, continue to improve the core technology and abilities, potentially to create things that are truly valuable and deliver them directly to customers, right? So really, it's this idea that there's a lot that can be done in terms of further development of photonic quantum technologies and photonic quantum computing. We want to get better at this. We want to scale them. We want to improve them. We want to have even better and better generations of those devices and do our best to design them and to program them and to guide them in such a way that they are useful to people throughout industry, academia, government labs, etc. So,
hey, Juan Miguel, there's already a question for you.
Okay.
So from Marcos Rizzo. So Marco is asking, what are the main challenges to scaling this architecture up?
Okay, I appreciate it. I don't have access to the chat right now, so if you could mention this in the future, and please I welcome questions. There are several challenges. The biggest one that I'm aware of is the fact that so there's two aspects to this generation of devices, right? There's the squeeze light and then the interferometers. And the amount of components in the interferometers scales quadratically with its size. So you can think of it as an area, right? So we want to have more modes, then we have the number of components scales quadratically with the number of modes. And these are things that we control electrically, right? Or thermally sometimes, but they require some electrical signals to be able to control them. And that pumps in a lot of power into the device. So that's one of the challenges, and it poses to some extent a fundamental limitation on how big these devices can be, because it's very difficult to fit them in a two-dimensional structure, and it's very difficult to limit the amount of power, so without heating the device so much that it stops functioning as you want it. So there's a limit in this regard, but there's also one way of getting around it, which is to start using different kinds of modes, and in particular to go into a time domain. And part of what the architectures team that I mentioned before, one of the focus is to understand how to do this optimally. So essentially, there are different architectures that would use at their core the same building blocks of integrated photonics to build time domain loops. So it's really about just being able to control devices at this scale. That's very challenging. And of course, losses accumulate as well as you increase. So eventually, one would have to develop ways of correcting for that loss. These are the main challenges. Okay, so if there are no other questions,
He says that Marco says thanks. So
okay, you're welcome, Marco.
Yeah.
All right, so that was a bit of the intro to the company. So now let me tell you a bit more about our software. again, I invite you to take a look at the website. It's really full of amazing material. So if you really want to learn, like, everything that you need is there. But I'll do my best now to also give you an insight. So first, some primer on photonic quantum computing. Quantum computing is just, when you think of it fundamentally, it has two components, right? One of them is this idea that we can encode information in quantum systems, and quantum states now are different than classical ones. So we have superpositions, and we have entanglement, etc. So it's really freedom in how we encode that information into degrees of freedom of physical systems. And then we process that information, and we process that information by applying transformations, right? And we typically think of them as gates. So essentially, photonic quantum computing is quantum computing, like all quantum computing. The only thing that changes is that the way we encode information is slightly different. So even though there are ways of having qubits inside of Q modes, in a sense, it's a bit wasteful, because a single Q mode, so optical mode of the quantized electromagnetic field, actually has many more degrees of freedom that are naturally accessible. And there's a way in which we can exploit them, right? So typically you can think of photon numbers as being that degree of freedom. And so when we do that, we have systems that look more like Q-dits, so D-dimensional systems, except that D is not fixed. Essentially, you always have D+1 as a possibility. And so this is what happens when we take very seriously how to exploit as much as possible all the degrees of freedom of optical modes. So the math changes to some extent if you want to be serious about this. Secondly, that also means that the form of gates changes to some extent, right? So the idea of using CNOTs and Hadamards, T-gates, it's not what's most fitting. So instead, there's different classes of transformations that therefore are the components in how we process information through transformation in different gates. And oftentimes, it's good to visualize them in terms of space representation. So if you're not familiar with it, it doesn't matter too much. But we can think about how Wigner functions, essentially, of states of optical modes get transformed by these gates. And so some typical gates, and we will touch upon some of these later, are displacement. We essentially change the mean of the distribution signaled by this Wigner function. You can also squeeze. So essentially, you decrease the variance in one direction at the expense of increasing it in another one. There's rotations. So if you don't have a zero mean, you can essentially move around the center of phase space. And then beam splitter operations, which are the entangling gates, right? And they're literally physically half-tilted mirrors that transmit and reflect some of the light. So it's really quantum computation as usual, except that the fundamental systems are slightly different than qubits, and the family of gates that compose the computations are slightly different. But that's it. So we're going to build programs and that allow us to create quantum circuits using these fundamental building blocks. And so what I'm going to tell you is how the syntax works within StrawberryFields, right? And the main abstraction here is the idea of programs within StrawberryFields. And they're the object with which we declare these quantum circuits, and with which we actually design and specify them, right? And within a program are operations, right? So that's just in the technical name given to what we otherwise would. So examples of operations, are for gates, right? But it's a bit more general. You can also do things like measurements, right? There's also ability to do post-selection, etc. So operations are a bit more general than just gates, but they are the specific things that we do, right, when we specify an algorithm, essentially. The syntax is very straightforward. You specify the operation, then there's a vertical line, and you then declare on what subsystem this acts, right? So in what mode, essentially. Maybe it's in all of them, maybe it's just in a few of them, maybe it's a pair of them. And so this can contain all classes of things, right? Not just so how you can prepare states, gates you can apply, measurements, channels, and more. So let me give you a little bit more details and maybe take it a bit slower. And I will take a small break to drink some water. So first, StrawberryFields Python library. Therefore, pip installable. So if you're familiar with pip, just go to your terminal, pip install StrawberryFields, and you're done, right? And so within Python, we import as usual. The abbreviation that we typically use is SF for StrawberryFields. In this example, we're just going to import all the operations. That's not necessary, of course, in Python, but it just makes it a little bit less clunky when defining circuits, that we can specify the gate directly without having to say for example, sf.ops.gate, right? So these are the first lines of this code, just importing and making our life a bit easier when calling gates. Then the first step in declaring a program is just giving its only input, which is the number of subsystems, so in our case, the number of modes, right? So, and then within this program, we will declare the circuit. So there's this line. So the first one's not really necessary. You could just say sf.program2, but just for clarity, it's specified this way. So we initialize this program just by specifying the number of systems that our circuit is going to be composed of. And the only part like tricky, and maybe not completely standard, is that we employ, or StrawberryFields employs a context manager to apply the operations. What this means is simply that you start specifying your circuit with this line that says with prog.context. So if you remember, prog was the variable that we assigned to our program, so just the shorthand for it, as q. And this q is anything you want, right? So we use q to signify q modes in this case, right? That's the only line. And within it, then you just declare the operations that you apply in your circuit with the syntax that I explained previously, of the form operation, then vertical line to tell you on which subsystem it's acting, right? So in this case, we are applying a squeezing gate with squeezing parameter 1 on the first Q mode, then also a squeezing gate with the same parameter on the second Q mode. We're interfering them in a beam splitter gate. So I think, yes, I can explain a little bit more here. This gate has some default parameters. So in this case, you will have a 50-50 beam splitter. Half of the light is transmitted, half of the light is reflected. And this is an entangling gate, right? So it's an interaction between the modes. So it acts on a pair of modes. So here we declare which two subsystems these are in this tuple, first and second one. So again, squeezing, beam splitter gate, and then we just measure. So measuring is also an operation. In this case, there's no argument, so there's no default even. And Q, it's really a collection. So when we declare the program with the number of subsystem, the number of modes, internally it keeps track of that. So if you just declare it directly, it's equivalent to saying that it's acting on the entire system. So we don't have to enumerate Q0, Q1. If there were more, Q2, Q3, just Q is enough. So this last line is saying measure all the output modes and the fog bases. And that's it. That's how you compose circuits in general. So to give you the entire overview, this is a simple program that implements a circuit where we prepare two squeeze states, so squeezed vacuum states, interfere them in a 50-50 beam splitter, and measure the output. Right? It's essentially a circuit that prepares a two-mode vacuum squeeze state, if you're familiar with this. So this is how we write programs and how we specify circuit constructions. Then the second part of it is how do we execute those programs, right? How do we, for example, obtain the results of this fog measurement? And the main idea is that we use engines for this purpose, right? So this is just a technical term that's used to specify, you can think of it as the device, the machine, the object that carries out the computation. So typically it will be either a simulator or hardware, right? But it's about executing the programs. So this requires a little bit of, or it merits some explanation, because there are different choices of backends. Essentially, there's different kinds of engines. And one way of thinking about it is that the engine is run with respect to some backend, which is what is in charge of executing the programs. And again, this can be simulators or hardware. So let me start with discussing the simulators. There are three backends in StrawberryFields. So the first one is the Gaussian backend. This name comes from the fact that there are classes of states, Gaussian states, and Gaussian operations, that are given this name because in the Wigner function representation, these functions are Gaussian, right? And so Gaussian states are those that have a Gaussian Wigner function. Gaussian transformations are those that preserve Gaussianity, so map the Gaussian states to Gaussian states. So that's where the name comes from. That's also where Gaussian comes in Gaussian boson sampling, as I will explain later. It's a NumPy simulator, and it's built precisely for the cases where all operations are Gaussian, except we can still allow fog basis measurements, and then you use special, more efficient algorithms for simulating that specific case of preparing Gaussian states, applying Gaussian operations, and doing fog basis measurements. But in particular, because there's structure and symmetry in the state, is something we can exploit. So if everything is Gaussian, it's very efficient. If just the measurements are non-Gaussian, then it still scales exponentially in general, but it's much more efficient than a full simulation. There's also like the universal backends. So one's called the FOC backend. So this simulates all possible like universal operations on a collection of modes. It requires a cutoff. So essentially, what d of your qdit is enough to really encompass and to explain all physical behavior in your system. This, of course, makes it very difficult to simulate because, if you thought that 2 to the n scales very quickly, then d to the n is even faster if d is bigger than 2. But it's universal, right? So this is more closely related to universal photonic quantum computing. Similar to the FOC backend, there's the TensorFlow backend, which is really the same, except that it's built using the framework of TensorFlow, and in particular, that unlocks the ability to train quantum circuits more directly, right? So essentially, at the end, what you have is a big TensorFlow tensor to which you can apply all your favorites, like operations and optimizers, as if it were not something quantum, essentially, right? So this is like something that's built with the idea of being able to optimize circuits, right? We have some papers discussing how to do this. This is all really to be able to allow people to test and to benchmark access to hardware, right? And that's what I will explain later in this talk, and I will showcase later in the talk. I know I'm teasing you a lot about this, but it's on purpose. One difference, as you'll notice, is that we don't specify a backend in this case. So you don't go engine backend equals hardware or something. There's just a specific kind of engine called a remote engine that already, has inbuilt the idea that you're speaking to hardware. What you specify is what chip, essentially, what device you are running your programs on. So again, we'll touch on this a little bit later. So this is the backends, but let me tell you what happens when you run the programs, right? So you essentially declare that engine. So in this case, we're going to do a simulation we're going to use a simulator as our backend, and it will be the Gaussian backend. Because the squeezing gates, beam splitter, they're all Gaussian transformations. So the whole circuit is Gaussian. We want to exploit that. If it were not Gaussian, then some of these have backend options. For example, you have to specify the cutoff. So that's just a note to keep in mind. And then that's it. Like, you've declared the engine, you run it, right? So it's a very self-explanatory term here. You now execute the program on that engine. So as input, you have the actual program that we defined previously, right? And then as an additional argument, there's a shots argument that just tells us how many times we repeat the measurement, right? So in general, you may want to get statistics from your circuit, not just a one-shot thing. So you can do that directly from one line of execution, of running of the engine. And what happens is that you see these are stored in this results object, and from that we can access different pieces of information, right? So for example, when you're running in a simulator, you have access to the actual state of the system, right? Specified, for instance, as a Gaussian state, so it's a covariance matrix and vector of means, or perhaps it's a big vector if you're using some of the other, and if it's a pure state, if you're either using some of the other backends, right? Of course, if you actually perform the measurement, then you can obtain the samples directly from this results object. So essentially, when we run the engine, all necessary information is stored in this object that we're just calling results in this example, right? And so this is the entire workflow, right? This would be simple code that executes a version of a hello world program within StrawberryFields. Again, to summarize, we import the library, we import operations in a convenient manner. We initialize our program. With the context manager, we specify the gates and the operations that we want to apply. Then we declare an engine that's going to run our program, in this case with a choice of backend as well. And then we run the engine, and we read the results from the output of running the engine. I don't know if there's any questions at this point.
Any questions? I don't see any in the chat window right now.
Okay, so I'll just continue. Thanks, Patrick. This is very basic usage, right? But hopefully a lot of you are aware of the fact that as we want to...
actually, we did get a question, Juan Miguel. So we did get a question just now, I'm sorry. Carlton says, why use the with block instead of just function calls?
That's an excellent question. I'm not qualified to answer it. So I've been more of a user and also a bit more of a high-level programmer in terms of Strawberry Fields. I'm not sure. I think it has a lot to do with, it's a design choice, really, right? So I don't think it's necessary, right? I believe, and I may be wrong about this, that it's partly motivated for access to hardware specifically. So I think this makes it easier, but I'm not sure. I could ask the people that actually like made that decision and get back to you. It's a design choice. Okay.
He says thanks.
Thanks. You're welcome. I'll talk about something that I've been personally more involved with, which is, and I was trying to say, there's a difference between knowing how to program a quantum computer at a very basic level and then executing more complex algorithms, right? So one of the reasons, like even in our devices, right, we get away with giving more high-level orders, right? Like build this, boom, and there's a lot of things happening in the background that take care of this. So we want to allow something similar in our approach to quantum computation, where users can play and they can develop, they can test like algorithms, right? Without having to declare every single gate that composes the algorithm. And so that is essentially the philosophy behind the applications layer of Strawberry Fields. Angus, who's there in the crowd, he remembers when Tom and I were working on this. That coincided with his internship, right? I really invite you to take a look at a paper that's been published on this. So this is the title, just applications of near-term photonic quantum computers. And it's really, this paper contains all the technical information that you want, not only on like algorithms to run on near-term photonic devices, right? And some of the current ideas of how to do this, but also the accompanying software. And that's been a big part of the philosophy at Xanadu, which is we want to develop new ideas, but we also want them to be resulting in hardware capabilities that allow people to actually implement, test, and study these basic ideas, right? So they don't remain in the form of equations in a paper, but there's something that you can actually play with and use. So a lot of the technical aspect is going to be found in this paper. I'm going to give you more of an idea of the user interface of the applications layer. So before that, a little bit of like overview. So Strawberry Fields is mostly about declaring programs and then compiling them in an engine and running them on different backends. The applications layer is somehow like serving an additional purpose as a helping process, as an intermediary. And it's really aimed at implementation of quantum algorithms that are tailored for photonic devices, right? And specifically, this is for Gaussian boson sampling, and I will talk about this a bit more, which is the model for Xanadu's near-term devices, right? It's divided into modules aimed at specific algorithms. So the idea here is that if you want to work in developing and testing and applying a particular algorithm, you can essentially have access to everything you need within that module. You can just say in that module. That's kind of the philosophy behind it. So there's kind of a module dedicated to each different category of application, right? And there's some also like helpful additional aspects of this, which include the ability to just sample. So if we want to directly sample for GBS circuits, we can do it without having to declare all these programs, as I specified previously. We also have tools for visualizing, and in certain cases that are useful for benchmarking, you can load pre-generated data. So you don't have to actually run all these things. We give you some samples that we did ourselves on supercomputer time for hours, and you can have access to them just by uploading them, essentially. So that's the main kind of like framework and architecture. Let me talk about Gaussian boson sampling. So perhaps some of you have heard about boson sampling. You generate single photons, interfere them in a universal interferometer, measure them at the output. Gaussian boson sampling is maybe a next generation version of this main idea, where instead of having these single photon inputs, which by the way are very difficult to implement. I heard a beep. I don't know if that's a question. I will continue.
Oh yeah. No, there is a question. Yes.
Okay.
And it's from Kunal. So Kunal is asking, related to hardware, how many modes are currently there in Xanadu's hardware device?
Yeah, okay, so that's the second part of the talk. The device that I'm going to showcase, and it's the one that's currently accessible, has 8 modes. I can spoil that people are currently working on a 12-mode device, like right now in the lab. I think I won't get into trouble for saying that. And there's also design that has been sent for 24 modes. So again, you should expect rapid progress because that's built into the whole approach, right? Like once you get those core components right, once we know how to generate really good squeeze light with microring resonators, once we know really well how to design the interferometers, it's just a matter of sending like bigger designs to the foundry. So there's additional challenges that appear, but somehow the tougher problems are already dealt with, and you have to deal with some issues of scalability. So 8 is the short answer, 12 in progress, 24 also in progress.
Yeah,
So
he says thanks.
Okay, you're welcome. Now, so Gaussian boson sampling is like the next generation of just the first idea of boson sampling, and it began from an experimental motivation because having deterministic photons or single photons is very difficult, right? So that makes them inherently non-scalable. If you rely on a probabilistic way of generating single photons, well, if you want to generate many simultaneously to be able to interfere them, well, that scales exponentially badly. Whereas in principle, you can create squeeze light deterministically, right? So now, and when you do this, it's kind of this idea that, well, in the end, if you've squeezed light, maybe you've displaced the light as well, you interfere it, at the output you have just a Gaussian state, right? So all these operations are Gaussian, and therefore the output state that maps Gaussian states to Gaussian states, vacuum is Gaussian, it's also Gaussian. So what you're doing is you're probing a Gaussian state in the Fock basis, right? And these Fock measurements are non-Gaussian. So if you're familiar with like Gaussianity being efficient to simulate, we can break it just through the measurements. So it's really about, so it's specialized photonic hardware in the sense that it's not universally being able to control all possible degrees of freedom of optical modes, right? One way of thinking of it as well, it's a specific ansatz, right? So it's a specific layer of sequence of gates, and so we can get really good at building these, and we know that they're difficult to simulate, and understanding how we can use them is part of like the question of developing algorithms. And so what happens is you essentially sample from complex distributions, and complexity in the sense of intricate, difficult, right? Complicated. But the main components are always the same three. You have generation of squeeze light, then interferometry to interact with different modes, and then detect photons at the output, and with the ability to resolve the number of photons at the output. And again, I guess that's what it's explained here. Squeeze light, fully programmable interferometer. So that part is completely universal. You can do any interferometer. Mathematically, this means that you can represent interferometer as a unitary. So we have the ability to encode any unitary into the circuit. And we resolve the number of photons at the output. Now, one of the beautiful things about this model is that we can actually write down a formula for the output distribution, right? So here S, think of it as a vector with components S1, S2, Sn, if we have n modes, and each Si denotes the number of photons detected in mode I, right? So we would have seen S1 detectors in mode 1, S2 detectors in mode 2, etc. So we're sampling these photon patterns, right? That's what happens when we make a measurement of a collection of modes in the Fock basis. We just get a pattern of photons. And this is quantum computing, so there will be a distribution. Each output will be probabilistic inherently. So there is a probability distribution that characterizes your circuit and the results of your measurements. And it's given concisely by this formula. So this alpha, you can ignore it for now. It's a normalization constant. It depends essentially on the overall total mean photon number in your distribution, which is something that we can play with effectively. These factorials that appear in the denominator, it's just a technical correction. It's essentially so things are normalizable in the end. But at the core of this formula is this formula, this Hafnian of AS, right? So A is a symmetric matrix, n-dimensional if you have n modes, right? It's symmetric, and it depends in a specific technical way on your choice of squeezing levels, how much you're squeezing each of the input vacuum modes with the squeezing operations, but also the specific settings of the interferometer. Informally, the squeezing levels are related to the eigenvalues of this matrix, and the interferometer unitary is related to the transformation that diagonalizes the matrix. The subscript S signifies a submatrix of A, and how is that submatrix built? It's built by selecting specific rows and columns of the symmetric matrix A. So essentially, the probability of observing a specific output is determined by this function, the Hafnian function, of a matrix that is specified by the pattern that you observe. So given a pattern, there's a particular submatrix, and you plug that into the formula to get the actual probability, right? Now, this Hafnian is something that I explained in the next slide. You can think of it for now as a generalization of the permanent. In detail, this is the mathematical definition. So similarly to what we do with the determinant or the permanent, you can express it as a sum, like a sum combinatorial sum, over products of different entries of the matrix. It doesn't matter too much. This is why you know that it's a complicated function, right? What's more important is that it's easy to show based on results from the permanent that the Hafnian, so essentially computing the Hafnian, even approximating it to within some approximation ratio, is sharp p hard problem, right? So for those of you that are familiar with complexity theory, this is, or even those that are not, informally, the class sharp p of problems is in a way a generalization of NP, that instead of looking at decision problems, it's counting problems. So in a way, it's even harder than NP. So sharp p hard is even harder than NP hard. Again, it's very informal, but it's a good intuition. And so what that means in practice is that all known algorithms to calculate Hafnians in a general setting require exponential time. And this fact, similarly to what happened with Boson sampling and the permanent, has been shown to argue, has been used to argue that simulating this Gaussian-Boson sampling model also requires exponential time with classical computers. So at the very least, we know that in building these devices, we are unlocking, in principle, the capability to perform a task that is otherwise intractable without the use of quantum devices. But the definition of the Hafnian is easier to understand when the input to the Hafnian is the adjacency matrix of a graph, in which case it's just equal to the number of perfect matchings in the graph. So let me explain that. First, an adjacency matrix. So a graph is a collection of nodes, in this case A, B, C, and D, and edges joining them, right? So in this case, there's an edge, for example, between A and D, between B and D, etc. And you can represent a graph that is unweighted, so we don't assign weight to the edges, which is clear there's a connection, with a symmetric adjacency matrix, where essentially the off-diagonal entries of the matrix are either 0 or 1, depending on whether or not there is an edge connecting the corresponding nodes, right? So if you look closely, the adjacency matrix on the right is the one for the graph on the left. And because it is, so importantly, because it is symmetric, we can encode it into a GBS device, right? So there's a way of relating graphs to these distributions. But given the fact that the matrix is the adjacency matrix of a graph, if you compute its Hafnian, right, the value of the Hafnian is exactly the number of perfect matchings in that graph. A perfect matching is it's a collection of edges in such a way that all nodes in the graph are connected exactly to one other node. So essentially, they are paired exactly with one, and this is true for all the nodes, right? And so the number of perfect matchings in the graph is the number of possible such collection of edges that satisfy this property. So it's called perfect because it touches all pairs of nodes, right? And it's a matching because it's pairing or matching pairs of nodes. So for instance, for this particular graph with specific edges, there are 3 possible perfect matchings as outlined here, right? So there's this pattern and this one, etc., right? So if we were to take this graph, create its adjacency matrix, and then compute its Hafnian, the answer would be 3, all right? And so now what I want to show you is this is a bit of an overview of Gaussian-Boson sampling. The idea, and this has been a lot of the research that I've done together with the help of many people, Tom in particular as well, on how we can be smart about encoding problems, about programming these devices to do something non-trivial, right? So essentially to carry out an algorithm. And the applications layer, StrawberryFields, is entirely built around this idea, right? What are different ways that we can program these devices to perform specific tasks? So I want to give you an example of one such application and also explain how you can write code within the applications layer to carry out the algorithm. So this is the problem of maximum clique. So what's max clique for short? You're given a graph. A clique in a graph is a subgraph, so it's a subset of the nodes, and you keep only the edges connecting nodes that you have selected. And this will be a clique if all possible edges are actually present. So it's a complete graph. There's no edge missing in this subset of nodes. And the maximum clique problem is the problem of finding the largest such clique in a graph, right? This is an NP-hard problem, so we don't expect, or NP-complete in its decision version, we don't expect even quantum computers to be able to solve it efficiently, but we can develop heuristic algorithms. And I'll explain how a GBS algorithm works for this. So again, the idea is we have a graph. A clique is a subgraph where all the edges are present, and we want to find the largest possible. And so the way the GBS algorithm works is as follows. It's a hybrid algorithm where essentially the device is used to seed a local search algorithm for cliques. So let me explain. The first step is we've learned how you can encode the graph, right? If you go back a few slides, any symmetric matrix can be encoded into a GBS device, right? And so if you can encode any symmetric matrix, you can encode any adjacency matrix, therefore you can encode any graph. So we just encode the graph into the device, right? And what happens is that there's a connection between the Hafnian and the density, which is the number of edges in a graph, that tells us, and it's a very important property of Gaussian boson sampling, which is that if you remember, the probability of getting a certain output is related to the Hafnian of that subgraph, right? So the number of perfect matchings. But what happens is that if a graph has a lot of edges, a lot of connections, it has a lot of potential perfect matchings. So essentially, the graphs that have large Hafnian, they also have a large number of edges. And when you're trying to find subgraphs that have the maximum possible number of edges, so these cliques, these complete graphs, this seems like a very good idea. And it's true. And we have a whole paper showing this, where there's a connection between the probability of sampling a specific output, which corresponds to a subgraph in a GBS device, and the density of that subgraph. In other words, GBS, when you encode a graph into the device, you can associate subgraphs with the outputs, and the outputs that occur with high probability are those that correspond to graphs that have very high density, a very large number of edges. This is great if we're trying to find cliques that have a lot of these edges. So the idea is we encode the graph into the device, and we generate samples. To each sample, as explained here, depending on which detectors actually have photons in them, every time a detector has at least one photon, we pick a corresponding node of the graph and generate a subgraph. So here it's shown by these yellow nodes. That's a subgraph. Again, by properties of the device, this will have high density with high probability. This is good. It's not enough. It's not going to be a clique. It's not going to be the largest clique right away, right? But what we can do is we can then carry out classical strategies to find cliques. And the way these work is we can first shrink this graph by removing nodes that have very few connections until we actually find a clique. So if you notice here, initially the output had 8 modes that clicked. So that corresponds to a subgraph of 8 modes. This is not a clique, but if we remove 1 and 2, we end up with a clique of size 6, right? So we first shrink into a clique. And finally, there's a strategy where given a clique, you can search for other cliques in the neighborhood. You can ask, is there any node, any vertex that I can add and also get a clique? So I try to grow it. And when you can't grow anymore, right, you start trying to swap some of the nodes. So you also have a clique and you repeat that. So it's kind of locally from some starting clique. You can try to grow and move it, alter it, and keep trying to grow it in sequence. So maybe the details are not too important, but there's the idea that starting from a clique, you can do a local search. So if we can generate an already very dense subgraph, we can shrink it into a clique and then apply this local search, right? And that's a GBS algorithm. And the idea behind here is that initialization, finding where to start that search, is very difficult classically. And what people actually do in practice is they just do uniform randomness, because essentially any other strategy has pitfalls. right? It's greedy and doesn't usually work very well. So what we do is like, well, we have a device that can actually give you good starting points, right? So let's just use it. And you can test how it does give rise to quantifiable improvements. Here's the implementation in the applications layer. Let me just check time that I'm not going too much overboard. We should be good. First, as a parenthesis, we can generate samples from the device immediately. So we don't have to go and declare a StrawberryFields entire program. We can call in built-in functions in the apps layer to sample from GBS distributions. So in this example, so first, the apps is its own module. So you will import parts of the apps layer just through strawberryfields.apps. In this case, we're importing the sampling submodule. And there's the sample function at the end, which takes as input a symmetric matrix that describes the distribution. There's also a mean photon number, so a total mean photon number, which is something that we can also configure in the device. These two are enough to fully specify the circuit, right? And then we simply generate a certain number of samples. So in this case, what we're doing is we are looking at a device with 5 modes, with a total mean photon number of 5. We want to generate 10 samples. So what I've done here is generated some random symmetric matrix, and then we can call this one-line sample function to generate 10 samples in this case from it. So it's much more straightforward and more closely connected. And importantly, it takes care of the decomposition of, given that symmetric matrix, how to specify squeezing levels and interferometer, which is not always completely straightforward. So that's also built into the apps layer. But now to run the algorithm, this is it. The max click algorithm that I mentioned is just these few lines of code. And I believe, yes, it's all here. I'll go very quickly. So we'll work within the click module, which is built for max click. We'll look at the data module to be able to load pre-generated samples, right? So we'll use it to benchmark. And sample just allows us to also apply some post-processing on the samples, right? And because we're working with graphs, it's useful to employ Network X, which is another program. But essentially, in the data module, we can load a class of data called p-hat. It's just the name of a specific graph. From that, we can obtain its adjacency matrix and convert it into a Network X graph, right? Now, this p-hat that we loaded from data is a collection of samples. It's loading the samples, right? Something we want to do is we want to post-select them, so we don't want outputs that have too few photons in them. They're graphs that are too small. We're trying to find the maximum click. We also usually don't want them to be too big, because then there's a bit too random. So we can post-select, and we can do this with a single line, and in this case, we're post-selecting of outputs with 16 to 20 photons, okay? So again, we load the samples, we specify a graph that's going to be used later, and we post-select the samples. There's a technical step where we convert these samples into actual subgraphs. So remember, I told you that associated to each photon pattern, there will be a specific subgraph. So this takes care of that immediately. And then the shrink and search functions, they take care of these additional steps of the classical algorithm, where we're taking these post-selected samples, shrinking them into a clique. So we get a list of cliques, and they are each fed into a search algorithm that performs, in this case, 10 steps of local search to find larger cliques. At the output, we'll have a collection of cliques. And what we can do, for instance, is sort them out by size, right? And then print the largest one. And again, there's built-in functions for plotting graphs. So if you think this image on the right is really nice, well, that's like the default of what you can use within StrawberryFields. And this is an example of the output of the largest click that was found by this algorithm, right? And this graph, this p-hat, is part of a standard benchmark data set where we know what the largest one is, and we can check that indeed we have found a click of the largest size. So an algorithm that might otherwise be very difficult to implement, because you have to figure out how to encode your graph into the device, you have to figure out how to generate the samples and write your program, and you have to actually create all these steps of classical algorithm. That's taken care of for you. So you can worry about the problems and about finding good solutions and about like improving these basic capabilities. And this is the philosophy of the apps layer. I gave you one example with Max Click, but this is a bit more wide. And again, there's a lot of documentation, a lot of tutorials for different applications. This is also ongoing. It's part of my work is to expand this as much as possible. I urge you to, or invite you, let's say, to take a closer look. Okay, now it's the main event. I don't know if there are any questions at this stage.
Yeah, there is a question
Okay.
from Carlton,
Mhm.
which is, did you benchmark your max click solver next to established classical approaches?
Yeah, so in a way we are cheating because the algorithm that I just proposed, that I just mentioned, is actually based on the best algorithms for finding maximum click, right? So these local search algorithms, they are the best ones. So what we're saying is we're not trying to have a fully quantum algorithm, like we're not trying to do some, say, QAOA to find max click. We are trying to improve classical ones. And so then the question is, can you actually really improve at all, right? Is the seeding from the GBS device helping? And that is not so clear. The answer is essentially it depends. But what we've seen, and there is a specific paper, and I can send you the link. It's molecular docking with Gaussian boson sampling. So it's a specific application of max click, where so that's one of the papers that we can see actual results, where in specific cases we can build a version of this local search algorithm that is performed as usual, where that seeding is purely classical, and compare it to a seeding from GBS devices for small graphs, and you see increased performance. It's not like an exponentially better one, but it's very noticeable. So for instance, you can have a figure of merit of how many steps do you need to find the maximum click, or what is the chance that if you've run 100 versions of this algorithm for different initial points, that you actually find the maximum click. And you can see like a percentage improvement, right? So maybe the purely classical strategy finds the maximum click 20% of the time. And if we see that with GBS, you get maybe 20, 50%. I forget the actual numbers. So not only have we, so to answer your question, not only have we compared to state of the art, but what we've actually done is we've had an approach of trying to improve the state of the art. What's not clear is whether you go to different instances, where you go to harder problems, if you still find that improvement. But it's built into the design of this approach that you're leveraging as much as possible existing state of the art.
Yeah,
Alrighty.
good. There's one more question from
Yes.
Marco, and Marco is saying, even if heuristically determined, is this improvement polynomial, logarithmic, etc.? Or do you basically he wants to know
We don't know.
Yeah,
We don't know. We don't know. And that's an excellent question. It's maybe not too hard to believe that it's a frequently asked question by referees. My answer at this point is we don't know. It's very difficult to determine this because, like, essentially any analytical results related to GBS, they stumble upon the appearance of the Hafnian, which is monstrous to deal with, and so any kind of asymptotic results are very difficult. Something that we have, so the closest that we've come to that is showing that if you compare uniform sampling to sampling from a GBS device, then essentially the average density of your output grows like the square root of, so the ratio between the size of your output, the density of your graph compared to a uniformly sampled subgraph. If you look at this ratio, so the bigger that one is, the more that we are sampling denser graphs with respect to a uniform baseline. That grows like square root of n if you program essentially a random graph. And it's only for random graphs that you can make like asymptotic statements. So there is like a square root n sort of like hint that that's kind of like the additional bias and advantage that you get. But when it comes down to, like say the time complexity of an algorithm that solves the problem, we don't really have the answers to that. And so, but that's a very interesting question because that's a philosophy of benchmarking and understanding quantum algorithms that I think is being very questioned by the actual appearance of devices, where we can just like not care about these kind of things and just deploy algorithms and kind of test them out, right? And so what we've tried to like to showcase in our publications and demonstrations, it's more like, look, here's a new technique, we try it out, and it has this performance, right? And of course, being able to have that support from the theory of saying like, oh, you can get cubic advantage asymptotically, that would be fantastic, but it's very challenging. And I think it's an interesting question, the extent to which it's it's relevant when, regardless, we're always working with finite sizes. But maybe it's a bit philosophical. And long story short, we don't know, and we have a little bit of a clue of, in some cases, a ratio that grows like square root n. Okay, thanks. That's a thanks. Or another question?
No other question. He just said thanks.
Thanks. Okay, I thought so. Good. So main event. I'm excited about this. So first, I want to tell you about the device. So it's actually the same picture that I showed you before. So somebody asked how many modes. So in this case, it's an 8-mode device with an asterisk. So really, so optical modes come in different forms, right? So they can be distinguished spatially. So essentially, light traveling in different coordinates, almost like in different locations, different lines, different wires. But we can also have modes that are different in shape, also modes that are different in frequency and time. So the way that squeezing is generated in this generation of chips, it's what's called non-degenerate squeezing. And so what it means is that what you have at the output is really a 2-mode squeeze state, for those that are familiar with this term. And these 2 modes are actually different in frequency, right? So if you look at this device, there's actually 4 modes, and you can see 4 resonators, right? 4 rings. So there's 4 spatial modes, but within each mode, there are 2 frequency modes that are traveling, right? And we can probe those independently at the output. So the fact that we're using frequency means that there's a bit of a restriction in terms of the operations that can be applied. As you'll see, it's kind of like a block unitary that's being applied. But it's overall, we have control over 8 modes, and we can importantly probe them, right? So when we say interferometer gate depth equals 4, it's really like saying there's 4 spatial modes. The squeezing factor, so this parameter R of the squeezing gate, if you're familiar with this, it's approximately 1.14. So there's a bit more than 1 photon on average being generated at the source for each squeezing mode. There's significant loss, as you can expect, about 85%. But as you'll see from the example, we still generate a lot of photons at the output. The squeezing is not tunable, so we cannot set that squeezing factor to any value that we want, but we can turn it on and off. So that's some ability that we have. And technically speaking, you can characterize the quality of squeezing level by what's called the G2 factor. It's a bit technical, but ideally you want it to be 2, and we can show that it's bigger than 1.8, and probably even higher than this. So it's actually really high quality squeezing, and like a very proud achievement of the hardware team. So this is the device that we're going to be accessing. And I really want to drive across the point that sometimes it's easy to like take technology for granted, but I've been in this game of like optical quantum information processing for long enough that I've seen what versions of this look like in the past, where you had labs, usually in universities or maybe in industry as well, run by like dozens of students, postdocs, PIs, with huge optical tables full of elements, right? Like extremely complicated, really difficult to control. And like we've come to the point where it can all be miniaturized, right, in a single chip, potentially mass produced. And importantly, that people like myself that shouldn't really be allowed in a lab because things can break, we can have access, right? I can just send a few lines of code and run a quantum optical experiment. So that's really what we're doing. And this is a real achievement for photonic quantum computing in particular, right? But in terms of like quantum optics in general, so this ability to control and to manipulate quantum optical systems in a way that's reproducible, in a way that can be scaled massively, and that can be made compatible with like remote programming is something that's very unique. So this is essentially replacing an entire lab in a department. Of course, there's an entire lab at Xanadu, but all the magic is happening within a single chip. Was there a question, maybe?
Yes, there's 2 questions about loss. The first question is from Kunal. How does the GBS perform in the presence of 85% loss?
Yeah, so that's an excellent question. The answer is we don't really know exactly, but what happens, it doesn't help, obviously, right? So it kind of depends on what you're trying to do. And some different applications, some different use cases will be more or less tolerant of loss. So for instance, the example that I mentioned with Max Click, right? It's one that it's relatively speaking noise tolerant. And again, in this paper that I mentioned, we actually benchmark that. So we actually test what happens with when we simulate loss, how do things change? And essentially, the intuition that you can have is that you can imagine loss as being like some mixing of your distribution with some background noise distribution, right? But as long as you still have a signal, right, you may still be doing better than pure noise, right? So essentially, it's like you're kind of diluting the quality of your outputs, but there's still enough in those outputs that can still be useful. So for instance, when you look at these metrics of how do we compare with just uniform loss, uniform randomness in selecting subgraphs, what you see is that you increase loss and essentially you kind of do a bit worse, but you're still doing better. There's other applications like vibronic spectra that I will touch upon a little bit on the demo that are perhaps like less tolerant of loss, and that can be a real problem. So, and of course, loss in photonics is the same as, it's just the dominant source of noise, but this is true of all quantum computing, right? So I don't need to tell you and this audience that we have hopes that in this era of noisy devices that are small scale, that there's things that we can extract, but there's always the possibility that you eventually need, in specific cases, to just correct for that loss. And it's in principle possible, but it's just more challenging.
Yeah. Hey, Carl says thanks. Carlton also has a quick question. Is the loss IID? Is the loss IID? Is Carlton's question.
I mean, it's a great question. It's a great question. Maybe IID is not necessarily the way to think about loss, but essentially the question is like how to model that loss, right? And so the crudest version of that loss is that you have a perfect device, and then at the end you apply a loss channel, essentially, right? Something we can model mathematically. Happens all the time in QKD, for instance. So that's one version. You can ask, is that a good model? Well, no, that's not good. First, loss is not really uniform across every mode. So maybe that's touching on your IID. So you don't have just like the same loss on every mode. In general, it can be different in each of them because of imperfections in fabrication and like details of how the device actually functions. And also, it doesn't always happen uniformly at the beginning at the output. So my best answer to your question is that the best noise model in terms of modeling loss is one in which the loss is different in each mode, and it's also different at the beginning and at the outputs of the circuit. There's other parts of the circuit where loss commutes, so it's not so important, and that's like the best form of it. But it's a very specific loss model.
Okay, he says thanks. I mean, it kind of sounded like the question was like, is there, I don't know, I could be wrong, like crosstalk, like, but it sounds like there's no crosstalk really, right? So it's in that sense, it's kind of independent, right?
As far as I understand, yes. Losses in particular, yes. There's other forms of errors. So for instance, when you set the beam splitters and rotation gates and the interferometer to specific values, they aren't always done perfectly. And in that sense, there is a bit of crosstalk in the sense that it's the usual problem in quantum computing, right? We want to act and we want to interact with quantum systems while not entangling ourselves with them and preserving them, right? And not entangling components that we don't want that to happen. So there is a bit of effects of crosstalk in the sense that when you set a specific value for one component, it may affect how well you can do it elsewhere. But my understanding is that these are very small errors. So photonics is kind of interesting in the sense that the elementary gates are extremely high quality. So these beam splitter rotation gates, they are fantastic. The problem is there's loss always. So it's really, that is the thing you have to fight against.
Cool, thanks. Keep going.
All right. So mathematically, in terms of a circuit diagram, this is what the device is doing. So we have 8 modes from 0 to 7. You can imagine that you have vacuum coming in, and then this initial part before the U4 interferometers, it's really preparing 2-mode squeeze states, right? But one way of doing that is to have like squeeze states on a pair of modes. So for example, the 0th and 4th mode are squeezed with the same value R0, right? And then they interfere in a beam splitter. And this beam splitter is here represented in terms of this like 2 points with a wire. They may look familiar. That's exactly what we did in the previous example, where we prepared two squeeze states in the StrawberryFields program and then interfere them in a beam splitter. So that's what's happening. And that's what that's what these micro-ring resonators are doing, right? So there's cavity QAD effects going on, nonlinear optics effects occurring, and they generate these states. And essentially the modes on the top and the modes on the bottom they differ by frequency. So modes 0 and 4, they travel in the same spatial wire and the waveguides in the chip, right? But they are occurring at different frequencies. And so for each collection of these 4 special modes, we can apply an arbitrary unitary. We have full control over it, right? And then the output there are measurements. So when we actually want to send jobs to the hardware and to the chip, we do it through StrawberryFields. So it's the same as we saw before. However, if you notice, the important difference is that when we run the engine at the bottom, we don't call it the usual engine, but we just call remote engine. Okay? So that's essentially a specific class of engines that are tailored for hardware access. And then the input to the remote engine is a specific string that specifies the specific device, right? So this is in anticipation of us being able to offer different devices and different access. So you're going to have like premium, it's so premium, like a preview, right? A premiere of like the first device that can be remotely accessed, but the syntax is such that we can specify different devices, right? And the program is replicating what we saw previously, right? So we want to apply 2-mode squeezing gates. This is the S2 gate. We can actually specify whether they're on or off. So in this case, we're only squeezing the first pair of modes. In the program, I technically then therefore don't have to actually have these 3 lines saying that don't squeeze the last ones, but I want to write it down so you can imagine changing that squeezing level. So it can be 0 or 1, on or off, in any way that you want. And then we apply interferometers. This is any interferometer. In this example code, it will be a random interferometer that you can generate also within StrawberryFields. And we're making a measurement. So that's why we have measure fuck at the bottom. And when we simply declare the engine, we run it. And notice how we can generate a lot of samples. So one of the unique capabilities of photonics is that you're not limited by the speed of light, right? You're only limited by electronics, and in particular, that means that it's possible to generate like outputs at really, really high rates, right? So in the example you're going to see in a minute, we can generate up to like 400,000 samples very quickly. I think I'm going to generate only 100,000. And really the overhead is actually in terms of calibration of the device. Once that happens, we're sampling anyway at like several kilohertz, maybe even closer to megahertz. That is very easy to get like a lot of samples very quickly. But that's it. So we're combining everything together, right? So we have the language that allows us to speak to the devices, right? And then just using remote engines, we can actually access the devices, obviously with the right permissions and API keys. So let's do it. So give me a second. I have a notebook here. So the only thing that I have to do is I need to have my, so it's usually a TOML file that allows me to allows the service to know that I actually have access and permission to run jobs. So that's the only thing that I have to like be careful with. You should, I believe, have access to that. If not, let me know if you want to test. There's a question?
Yeah, there's a question. So from Carlton, on the hardware, what is the maximum shots per unit time one can collect? And how long would your 400K shots job take in wall clock time?
Okay, so you're going to see how long it takes in the example. I will need to get to you on whether this has changed or not, but my latest information is that in each job that you send, the maximum is set to 400,000. I believe this is mostly due to like our ability to guarantee like the quality of the samples. And also, we don't want anyone to generate too many because that can damage the chip. So you do want to cap it to some extent. That's a bit flexible, so it doesn't have to be 400,000, but that's a good thing to keep in mind. There's a cap at 400,000 samples. The exact clock rate, I'm not sure, but I believe that it's around 100 kilohertz or so. So really, you're going to see the time that it takes to generate these samples is mostly to do with like the classical component of accessing the device, checking the specifications, calibrating the device, locking the squeezers, right? Of course, I've simplified all the physics that happens by saying there's just a ring and all the magic happens there, but there's a lot that has to be engineered and there's a lot that has to be calibrated. So there's initial stages that take care of this, but the actual sampling takes a few seconds. So typically it will be around 10 seconds or less to generate hundreds of thousands of samples, right? So anyway, it's the usual Pythonic workflow. So we first, and everyone can see my notebook, right? So I'm going to just run to import all the packages that I need. In this example, I'm going to do a toy version of the vibronic spectra algorithm. I also invite you to take a look at the documentation and our papers on it. This is an idea that's one of the earliest algorithms for GBS. Junsuk Hu is the main author at the time in the group of Alanas Purugusik. And it's a quantum chemistry application. The idea is to understand a specific way in which molecules can absorb light when they transition not only by exciting electronic states, but also by starting to vibrate, right? So you also excite vibrational modes in the molecule, and that's the photonic part. So there's correspondence between bosonic systems. So the idea is there's a whole machinery there. I don't want to explain in too much detail, but essentially there's information about molecules that give rise to squeezing levels, displacements, and interferometers that correspond to some mode mixing that occurs. So again, it's technical, it doesn't matter. But importantly, there are certain unitaries corresponding to certain molecules that you would implement in the algorithm. And we're going to do that exactly, right? So I'm going to load, I have them saved in my local file. We're going to load some unitaries that correspond to specific molecules. In this case, C2H4, which I forget the name of the molecule, ethene or something. Maybe somebody knows. That's a specific molecule, and this is the unitary. It's a real unitary, so I'm printing only the real components. And so we're going to program the device according to the specific unitary, right? Which again comes from what you would do if you're performing the full vibronic spectra algorithm for this particular molecule, right? So it's a real correspondence with an actual physical problem that we're going to encode into the device. So I just loaded it. There's a question, I believe.
No, I just said ethylene. I just said ethylene just to.
Ethylene. Almost. I almost got it. So it's the same as before. So we initialize the program. It's 8 modes, right? We specify the gates. In this case, I want to get as many photons as possible, so I'm just squeezing all the modes, but you can change it. So if you didn't want to have any squeezing on the second pair of modes, you could also do that. You could also delete this entire line. I don't want to do that. I want to see a lot of photons in my outputs. And we're feeding the interferometer that we previously loaded here, right? So I have U is this unitary here. That is the input to this interferometer operation. By the way, this already takes care of the decomposition. So the device itself has beam splitters rotations. This interferometer operation already takes care of the decomposition in the background. And we're measuring the flock bases, right? So I'm just going to create this program. And as you see, the engine is just the remote engine. And I'm specifying the specific chip. So it's the X8 is the name, Xanadu 8 mode, first generation. I'm going to keep track in the time because I'm anticipating these great questions of how long things take. Let's generate the 400,000 directly, even though some of the other post-processing is going to be a bit more lengthy. And that's it, right? So when I execute this, when I run this cell in my notebook, what's going to happen is we're going to communicate directly with the lab, which is somehow like a few hundred meters from my home in Toronto. By the way, on the 33rd floor of a building. It's going to lock the squeezers, perform the calibration. It's going to set every single component of the device according to my specification in the program, generate light, measure it, record it, and send the results back, right? So I just sent it. You get this little announcement, so you know that it has been successfully submitted, and there's a job identification. So if you ever find any problem, if you ever want to do any debugging, you can always keep track of this, and for example, contact the team to maybe look at what happened in the device. So So it's good information to have in general. So we can wait a little while, and then
there's a question from Marco.
Yes.
Marco says, "What's the overhead in compiling new?"
It's very small. So essentially, there's very efficient ways of doing it. Again, it's all one way of thinking about it is that it exploits these specific properties and symmetries of Gaussian states. Interferometers are also Gaussian operations. And so compilation of interferometers is very efficient. For example, if you compare it to what happens if you want to compile a general unitary on a universal quantum computer, that can be very challenging. This is done very quickly. So if you noticed, when I actually run I can do it again, right? If I run the cells, then it runs almost immediately, right? And that implies that the compilation is also happening. So if you notice, we generated 400,000 samples in around 30 seconds, right? And so you also get this little announcement that your job has been completed. So yay. And I'm not going to print 400,000 samples, but let's print the first 100 of them, right? There you go. And I do want to highlight beautiful outputs like this where we can actually detect and resolve photon number, right? This is very difficult to do, and the detector technology that permits it is really cutting edge and part also of the core technology at Xanadu. And we have also really high photon number outputs like this one, right? And there's all sorts of tests that these have happened internally to show that the states that we're sampling from are not classical. So obviously I can generate a lot of photons from my light bulb, but not from squeezed light, right? So there, and we can verify this and we can quantify it. These are not published results yet, but we can do this to show that hey, this is actual sampling from non-classical light, right? So this is what it looks like, the output of your results. Again, we're sampling from this GBS distribution. And what I want to do in the end is to show a bit of more usage of the applications layer. So in the apps layer of StrawberryFields, there's this vibronic module that's suited for vibronic spectra. So we're going to use some of the built-in functions to build a spectrum. So you don't have to understand too much of the details behind the algorithm, but what we are going to obtain at the end is essentially a histogram with peaks of different energies. And these peaks correspond to absorption lines of a molecule when it undergoes these vibronic transitions. You excite electrons, but you also make the molecule vibrate, right? And so the only thing that's really needed for that is a specification of the vibrational frequencies of the vibrational modes of the molecule, both in the initial electronic state and the final electronic state, our samples, and then we can convert them to energies and create a histogram of the energies, which is our spectrum. So this takes a little while just because we have 400,000 samples, right? So I'm just going to ahead. And again, the plotting is also taken care of automatically by built-in functions. So it's not just the ability to run the algorithms, but also even to perform some form of visualization. I thought about, hey, do I use less samples to make this part quicker when I was testing? But the plots are more beautiful if you have many samples, so it's worth a little bit of a wait. And again, this is now purely classical, right? Just about building beautiful outputs. So you get something like this, right? Where this peak at 0 always happens. That's essentially when the no mode is excited. So it's kind of a built-in correction in the algorithm where there will be some specific frequency, but that we don't care much about. We care about what happens when the molecule also vibrates. And so there are all these other peaks that appear. These are specific lines, right? Specific colors of light that are resonant with the molecule. And this is what quantum chemists are looking for in terms of understanding properties of molecules, for instance, in things like photovoltaic cells and so forth. Anyway, so that's the showcase. We did all this by accessing a photonic chip in real time. And that concludes my talk. Thank you very much.
Thanks, Juan Miguel, for the wonderful talk. So a lot of people are saying thanks and giving you virtual applause right now.
My pleasure.
Yeah, so let's open it up to see if there's any final questions for Juan Miguel. So there's a question from Matthias. Matthias says, how is the calibration done?
I don't know. That's a good question. Maybe I should. One of the things that I should know, but it's. I know. So first, there's a lot of aspects of calibration. This I know, right? So for instance, when I know at the level of the photon detectors, what essentially you get at the output is some electric signal, and essentially not only the shape but kind of like the peaks of that signal are the ones that specify the photon number. So there's a lot of actual like work that has to be done in terms of being able to determine like what specific shape of this electric signal corresponds to what particular photon number. And there's a lot of like classical algorithm and maybe even some basic tools in statistics machine learning to do that very well, and it's a non-trivial problem. There's also just the usual kind of like intensity settings and like frequency locking of the so the way you typically so roughly speaking, how you generate squeeze light is you have a bright pump at a different frequency. This pump light gets trapped in the ring resonator and creates nonlinear effects by having high intensity fields inside. So light gets trapped, and that gives rise to like output light that's squeezed. But for that to work very well, you need to be very careful in matching all the frequencies and also the shape of the modes of the pump laser. And there's techniques that people use to make sure that that's happening properly. I'm not sure about the details, but in practice, what I do know is that it amounts to generating like hundreds of thousands of samples and processing them and making necessary changes. So essentially what happens before even we sample is that there's a lot of sampling happening as well. In practice, the device didn't quite measure 400,000 outputs. It maybe did more like 1 million.
Okay, there's a question from Kunal. How many, and Tia says, thanks. Kunal says, how many minimum number of modes should we have to show any sort of quantum advantage, assuming 85% loss?
Yeah, so it's an excellent question. I'm going to assume that by quantum advantage, you mean simply that what the device is doing cannot be simulated by a classical computer. And that's an ongoing question. There's a whole team that is working precisely on narrowing that down. And it's a complicated question because it depends on, as you can imagine, right? It is sensitive to loss. So maybe 85%, well, what happens if it's 80? What happens if it's 90? What happens if it's 60? It's also like being able to have testaments of having an advantage is very difficult because you want a combination of complexity arguments that support that what's happening in the device is actually something that in principle is difficult to replicate classically. So you kind of rule out efficient algorithms, but it's also about developing very good algorithms. So that's a trickier part, right? So how to best simulate GBS. Some of the work that has been done from Xanadu, and there's another library that's more for internal use called the Walrus. So let me even write it down so you can take a look. This has the best algorithms for simulating these devices developed. So it's a paper, I'm part of that paper that we developed those algorithms. But there's no guarantee that they're the best either, right? There's no guarantee. So there's a difficult question of like what's the best that the classical computers can do and what exactly is the bar for what you have to beat. So it's not an easy question to answer, but we know that we can have lower bounds, right? So probably something like 50 modes or so is not enough. It's more likely to be closer to the order of 100 modes, right? And of course, you need losses to not be too high. So, 100% loss is not good enough, obviously, but the right amount is difficult to pin down. But there's ongoing research as a whole team that's working exactly on that. And of course, that's one of the main future goals for the company, right? So as we scale and we improve the technology, we want to be able to plant that flag, saying like we built a device that is performing a task that you couldn't replicate even with classical supercomputers. So to summarize, we don't know, probably around 100.
Okay, great, thanks. Another question from Matthias. He says, Do you know if StrawberryFields allows for conditional operations? This means, for example, performing a measurement on one mode according to the outcome perform a conditional unitary
Yeah,
function on the remaining modes. Anyway, you know what conditional operators are. Yeah.
yeah, and I now have access to the chat. I needed to use different browsers for the presentation, so that's why I wasn't. But now I can see them. Yes, absolutely. This is built in. That's something that in PennyLane is not built in, just because the philosophy in PennyLane is about differentiable quantum computing, so that makes things a little bit different. But in StrawberryFields, it is definitely possible. You can look at one of the first tutorials is a tutorial on teleportation. And teleportation, of course, requires you to do it fully to perform a conditional correcting unitary based on the outcome of a specific measurement. So it does allow for this, yes. You're welcome. It's important because also one of the way of generating non-Gaussian resources is precisely through non-Gaussian measurements and then operations post-selected on specific outcomes. So we knew that from the beginning, that it was important.
Any more questions? So I think there was plenty of questions throughout the entire talk. So I think it went really well. Thanks, Juan Miguel. That was really awesome. So
thank you again for the invitation. Really my pleasure.
Yeah. So let's give Juan Miguel one more round of applause.
Thank you, everyone. And if you have any further questions, want to be in touch, my email is just juanmiguel@xanadu.ai, and Patrick can forward it as well. I'm happy to also talk more offline.
Awesome.
Thanks for your attention.
Thank you so much. And then we'll look forward to Tom's talk, which is actually coming really soon.
That's even better.
So